This video is about turning and centripetal acceleration. Up until here, the sorts of problems that we've done with acceleration deal with changing the speed of an object. If we have an object like this and it's moving along in this direction, we have looked at what it means when the acceleration vector points with it. That is for speeding up. And we've looked at what it means when the acceleration points against it. And that's for slowing down. What we have not done is look to what happens when we get an acceleration vector that points perpendicular to our velocity. This is how we turn. If this vector is completely perpendicular to the velocity, that means that it's not affecting the magnitude of the velocity vector at all. It's not affecting the speed at all. The only thing that this acceleration vector is doing is changing the direction that we're moving. If we apply this acceleration vector, then a moment later, our particle is here, our object is here, and now moving this way. Centripetal acceleration. Centripetal means toward the center. So if I have motion along a circle, if I am moving in this direction, so I'm moving clockwise, in order to stay on this path and not just keep going in a straight line, I need to apply an acceleration that is perpendicular to my velocity. That acceleration will point toward the center of my motion. Now it is possible that I'm not making a full turn, that instead of going in a full circle, I'm only doing, let's say this much of a curve right here. Well, that much of a curve still looks like it's part of a circular path. So what I'm doing is saying there is a radius of curvature of my circular path, whether I'm actually going in a full circle or just part of one. My path trajectory has its own radius of curvature. My centripetal acceleration will have a magnitude of v squared over r, and it will always point toward the center of my circle. That's the idea of centripetal acceleration, and I do want to look at how that works in a free body diagram, in an actual problem and everything too, even before getting to a derivation. One thing, this is a centripetal acceleration, and sometimes we come into physics with our own sets of knowledge and preconceived ideas about different topics. Sometimes you will hear in regular pop culture, regular media, about the idea of centrifugal force. Centripetal means toward the center. Centrifugal means away from the center. The idea here is that there is some force that points away from the center. A centrifugal force is not a real thing. This is not real. But it's what we call a fictitious force, or a non-inertial reference frame correction. Imagine if you are standing on like a merry-go-round. As you stand there and it goes around, if you roll an object right in front of you, it's not going to behave in the way that it would if you were standing on regular flat ground. Now, if this merry-go-round were really, really big to where maybe you couldn't even see that you were on one, you would assume that you were standing still, just on regular flat ground, and what you would see when you roll something is it being pushed and veering off to one side relative to you. It wouldn't make a whole lot of sense. In that case, you could, if you wanted to assume that you were stationary and inertial, you could rework all the math and ignore that you are on the merry-go-round and just make a correction for the whole world seems to be doing something really weird. That's where centrifugal force comes in. This is a concept that you will hit if you continue with physics and decide in undergrad you are going to major in physics. That's a concept that you really start to hit during maybe your junior year. So not for this course, not for anything you're likely to see unless you're going down that specific path. When I do this, I like to look at this in terms of centripetal acceleration, not in terms of force, because there's not some separate force that's doing this. If I have a mass attached to a string, maybe this is me standing like this, and I have a stick with a mass like this, and that mass is going to spin around in circles, right? So I'm now looking top-down view at this thing. So if I'm looking at a top-down view, here's my mass on the end, and here's the center where I hold my hand, and this thing is going to move in a circle. That's fine. This thing will move in a circle. I have, acting on this mass, tension force that points inward. This would just be a velocity. So when I write my sum of forces equation in the x direction, taking the right to be positive x, when I write my sum of forces equation, I'm going to get that my sum of forces is just tension. Tension is equal to mass times acceleration. And now I'm going to say, I am moving in a circle. I know I'm moving in a circle. So for acceleration, I'm going to put in acceleration equals centripetal acceleration equals v squared over r. That's all I'm doing with this centripetal acceleration business, is affecting the far right side of my Newton's second law equation. Now, I told you that I would give you a derivation. Here it is. Again, if you are comfortable with this idea, and I know this hasn't been examples yet, that's coming in separate videos. If you are comfortable with using the idea without really deriving it, that's okay, and you can skip this part. Here is the derivation. Imagine an object moving in a circle. And we're going to give that circle a radius of r. If the object moves a full circle around, then the distance that we cover is going to be 2 pi r. We can also look at the velocity vector. If the velocity vector starts out here, then when I go the whole way around, my accumulated change in velocity is going to be 2 pi times v. If I then look at acceleration as being a change in velocity over a change in time, my distance and my velocity are going to work out. I don't want to derive it.